we one weekend? You think we're going to make it two? I was talking to my little brother this morning. He's a student. He says nobody in his apartment complex is keeping the rules. I think we'll make it two.
What complexes you'd rather stay in?
Liberty on whatever that one is. That used to be the Elms on the corner there on 9th. One over by the brick oven there. I played basketball with him. He's telling me. Bishop had like a thing at someone's apartment. He said there were like 100 students.
Yep, the worst offender are the bishoprics when you get people to go.
That's terrible. I would have thought that they would have been the opposite.
Like in our church on Sunday, they're like, yep, and there's the youth, the devotional with Elder Rasbin. They're like, that would be a good time to get together in your family evening groups and watch it all together. And I was just like, okay.
Last thing I wanted to do is be a bishop. But I would have thought that he would have said, find like a group of 10 people, or your, you know, stick to that group, be social, but your group, kind of isolate, isolate the other group in that sense, right? Like, so your roommates and another, you know, department of people, or whatever your group is, right? Those guys kind of try and limit the number of other people. That's what I would think they'd try and do. Not get together for a week's activity. Let's see if we can get through this one today. How are you guys doing? I think that homework was too bad, was it? Risky when I say that. First homework, there's lots of plug-in. How are your other classes doing?
The last time you were asking how Dr. Pickett's doing, I was thinking about it. I think one big thing for him is he has all his notes printed, most of the stuff already written.
Oh yeah, so he's just, you're filling it in as you go. Yeah.
All of the important stuff is already written.
That's true. You gotta I don't know. I'm kind of against the printed notes thing. I kind of feel like the inefficiency of writing it is part of thinking it. Like if I just had the obvious duck squishing and stare at it, it's not the same as writing it when we're talking about it. I don't know. Maybe I'm old fashioned compared to that guy. This is the way I learned it. We're at 9 o'clock. Are you recording? I've been recording. Am I just sitting here, looking at my notes? Can I go on the internet?
Oh, we just cropped it.
I don't want to crop it. That takes forever. Why am I cropping it? It's going to be on there. All right. You're going to volunteer for the opening here.
Dear Heavenly Father, we're thankful for this day. We're thankful that we can be here at school to learn. We ask thee to help us to see clearly and bless us all to stay healthy. In the name of Jesus Christ, amen.
Amen. Yeah, so I found out that they're like, no, none of that in lectures. So I guess I'm on mask duty, which is kind of a bummer. I thought that was kind of nice, but oh well. But I'll keep the rules. Don't want to get into the hole. All right, so today we're going to talk about the last of our three transports. We're going to talk about that. Good. So I put the outline up there. Hopefully you have a chance to glance at it. I'll leave it up there for a little bit while we get started. Well, the first thing we're going to talk about is mass transport initiative law. Oh, I realized usually I put it on the microphone. I want to put that on. I don't know if that matters to anybody, but all right, how's that? Okay. Maybe when I mutter through my mask, you can hear me. Okay. So remember what we're doing here, right? We're talking about the relationship between the forces, right? The gradients of something and then the flux. We're trying to look at that relationship. And so I'll just write that out. About force and some generalized force flux relationship. Okay. And so our thought experiment here should be pretty familiar by now. We're going to consider, and this time we're going to consider a solid slab. The book uses an example of silica, so you can assume this is silica, and silica is pretty soluble to helium. So you assume that you've got some helium down here at some concentration and none up here, say you're nitrogen or air or something. Okay, so helium at some concentration, we'll call this WA naught. Okay, so it'll be the mass fraction. So A will be helium on this. So that would be A. Up here you've got WA equals 0. Okay. So I guess we'll rewrite this. So all right, this WA is equal to WA naught, and we'll say A is equal to 0. Okay, so we've got this slab of solid silica, and we've got some distance y, the thickness of the slab. We're going to put a coordinate system on here, x and y like that. And we're going to start this one off at time equals 0. And then we're going to look at what happens over time as we follow, so say at time 0, this is when we store, say, flowing nitrogen here. And then at time 0, we turn on, and now we're flowing helium. And if we plot the mass fraction here, so this would be WA0 right there, that would be WA equals WA naught. Okay, and over time, so at time 1, which is sometime later, we'll use that 0 as a reference, and then we had WA naught over here, and we've got some kind of curvy solution, okay, which we'll talk about translates that later. And if we come over here to time equals time 2, which is a much longer time, now we've got a linear profile. Okay, this one will draw. All right, and so this is an experiment that we're going to do, but we're just thinking it through and what happens. And so if you look at this and think about what the mass flux is through here, okay, you can say the mass flow rate, WAY, I think, divided by area, so the amount of mass flow divided by area that's going in there, that's going to be proportional to the delta WA divided by that distance y. Okay, so that this, that difference there. So that is going to be WA naught minus 0 divided by y. Okay, and so that constant proportionality is something that we're interested in. Okay, and that constant proportionality is going to be the diffusion coefficient, although they scale it by density to get the units the way they want. So we're going to put WAY per area is equal to rho mass density multiplied by this diffusion constant AB, and then we'll put WA 0 minus 0 multiplied by Y. Okay, and so that's a relationship between a gradient of concentration, okay, and the mass flux over here, and that's our basic constituent. All right, so we can rewrite this a little more generally and say the flux of A in the y direction is equal to, and if you look at this, you want the flux to be up, okay, but this gradient here, you have a time on the bottom, so to flip that sign around on the gradient, you put a minus in front, minus rho DAB, DWA, D1. Okay, so we're just looking at gradient. Okay, so that's fixed law. Okay, sometimes fixed law fusion, sometimes fixed first law. For the way, I don't know why it's a second law just for line conservation mass heatness. So, but anyway, so that's fixed law. Okay, any questions on that? Yes.
So when I was looking at this in the book, I had a hard time with diffusion. I always think that it would go like almost like a square or rectangle straight up, like it would diffuse evenly across the surface. What makes it so that it has that triangle shape?
Okay, so the actual mass is diffusing just up, right? It's that it's a higher concentration up here than it is up here, right? So this is, you can think of this as like, put it on like a z-axis or something, right? And so it's a high concentration here, but you need concentration to drive, overcome the barriers, or push more stuff in. Okay, right? That makes sense. Yeah. Good question.
Did you also say that we were flowing nitrogen?
So yeah, you're flowing like nitrogen up here. So you're maintaining the boundary condition up here at 0, right? And you're maintaining down here at some constant concentration, right? So at some point you have to reach a steady state, right? You can't put it all. So if you had, if you were allowed to fill up this over here, right? You could eventually reach a point where the concentration would be constant, but at the beginning it would be 0, and then it would sort of slowly increase, depending on how big your chamber was at here that you were filling. But that's sort of a different problem. Make sense? All right. So E is really quick for this. So we can write a more general expression. Okay, and now we just do what we've done in the past, right? So this, mass is a scalar. So this flux is a vector, right? We're looking at the flux in the y direction. So if we wanted to look at the flux relative to any gradient, we can write this the full flux vector. So JA is equal to minus rho DAB gradient of the mass direction. Okay, so we're simply here just writing the expression for any three-dimensional coordinate system, okay? And this assumes that we're isotropic, okay? So if it were not isotropic, we would actually have a diffusion tensor here. So we could rewrite one that was minus rho DAB with it's a matrix and do a dot product of A, that would be non-isotropic or anisotropic.
That's if you are just using it like that, like
Yeah, so that's a good example. So if you've got different diffusion coefficients in different directions of the tree. So crystal lattice might have that. Graphite that has sheets, maybe it's really easy to diffuse in this direction, but hard to go between the layers, something like that. Okay. For the most part, we're not going to deal with that in the class. All right. And then C is also pretty easy. Today's kind of like rehashing a bunch of the stuff we've done already, but just for mass. So on C, this one is diffusivities. Diffusivity ratios. And we already saw, I think it was the Prandtl number. So if you remember, the Prandtl number was the momentum diffusivity divided by the thermal diffusivity, right? Momentum divided by thermal. Okay, so now with the diffusion, the mass diffusion constant, we can define two more ratios, right, with everything else. So there's the Schmidt number, which is the kinematic viscosity divided by the mass diffusion, okay, which you could rewrite as mu over rho GAV, and that is momentum divided by mass diffusion, okay, and we can write the Lewis number, which is thermal diffusivity divided by mass diffusivity, which if you want to write it as a I can't remember what the word for K is at this point. K, what's K? Why can't I think of K? Thermal conductivity, thank you. Okay, so that's thermal divided by mass. Okay, so we like to play the dimensionless number game and transport, and there's a couple of them that we're going to see later. Any question there? It's been a riveting few minutes. So this is a little more interesting, I think. Thing we're going to do. So one of the unique things about mass diffusion, as opposed to thermal diffusion or momentum diffusion, I guess each kind of has their own thing. I think the easiest one is maybe thermal diffusion. The hard part about momentum is that it's a vector, so then you have to do with like tensors and stuff, right? The hard part about mass diffusion is that it's always a mixture. So you can never get away from having a mixture, right? So let's point this out in D. We're talking about self versus mutual diffusion. Okay, so the point here is that DAB is a property of a mixture. Okay, so that makes it a little unique relative to things we talked about, right? So I think there's a problem in your homework where you have to calculate the viscosity of some mixtures, and that's just kind of quite interesting stuff. But you know, when we're talking about diffusion, you can't get away from having a mixture, right? So there's at least one important point to make about the diffusion coefficient, and this relates to some of the prediction methods too, but it's also just an important concept to understand. So there are sort of two different parts of diffusion. So imagine I have molecules in here, and I'll just have these be little black dots. We're going to call this molecule A only. Okay, this sitting in a box. And we're going to compare and contrast that to the case where I've got molecules with A. Okay, will be multicolor through this will be setting. Okay. With molecules of B. Oh no, Martha, this is your time to shine. You gotta go now, man. Here we go. Okay. got molecules of B in here too. Okay, so we'll make these guys B. It's like something. Okay, so you can write down for A, these molecules in this box are still going to move around by Brownian motion. Okay, so Brownian motion is the kind of motion we describe with a single particle when it's colliding with a bunch of others. Okay, so it's going to move around and wiggle and have a random path. Okay, and so if you pick one spot in time and then watched it move around, it would still move. Okay, and still have some kind of transport. Okay, and so you can define what's called a self-diffusion coefficient, CA. Okay, so this is a self-diffusion coefficient. Okay, and the key here might be to think about this Brownian motion. Brown is a man's name, so he was a botanist, I think. He was looking at pollen grains in water in a microscope. I noticed them wiggling around. They went unexplained until 1905 when Einstein derived a theoretical expression for the diffusion coefficient of these particles that live in Brownian motion. Because one of his, Einstein had this year in 1905 where he had 5 papers. It's 5 papers, right? You should know. Okay, five papers that were all made important advances. The paper on Brownian motion essentially proved that molecules were real. So that was kind of a cool thing, okay? Because you finally had a connection between something that required molecular properties, which we can show and we'll talk about a little bit here, that was with the fusion coefficient and the molecular theory. So there have been all sorts of kinetic theory, but people had regarded at that time as something that just you didn't necessarily need, So kind of like people think about string theory now, there's sort of this idea, there's people have these ideas they can create, things that predict certain properties of atoms from them, all right? But no one necessarily needs it. So they're like, this is maybe a nice theory, but nobody needs molecules. And Einstein's papers show that it'd be good. Okay, the molecules in box 2, they experience a gradient. So you notice that, over here, I've got, if this was my concentration of A molecules, right? This would be like WA as a function of space, okay? And then I have WB that's going in the other direction like this. Okay, so that's going to be WB, right? So they have a gradient. Okay, so there's a gradient of WA, WB, all right? And that leads to a mutual diffusion. Okay, and we have a constant for that, which is DAB. Okay, and so it turns out you can write a relationship between these diffusion coefficients. I think it gives us in the book, but I remember DAB is equal to TA times 1 plus a derivative of the natural log of the activity coefficient. And I'm going to write this in terms of mass fraction or mole fraction. So this here is activity coefficient. This is the mole fraction. We'll talk more about in a second. Okay, so what this tells you is that the mutual diffusion coefficient depends on what the self-diffusion is, right? So that makes sense. Like there's random motion of these guys too, okay? But there's a term that relates to how they interact, okay? So if it's an ideal mixture, the activity coefficient is 1, right? And it doesn't depend on the mole fraction. And what happens is that these guys can't even feel each other, right? They can't feel that there's any kind of gradient because they don't interact. It's an ideal solution. And this looks just like self-diffusion. These guys just experience Brownian motion, and the gradient ends up going away just because they randomly mix over time, okay? But if they interact, this activity coefficient is not 1, all right? And then there's some extra effect here, how they interact as that gradient exists, okay? And that affects the total So it turns out that these are a lot easier to get. Sometimes these self-diffusion coefficients are called a tracer diffusion coefficient. And it's called a tracer diffusion because what you can do is say, put in some different isotope, right? So I don't know if you would do example of this experimentally because I'm not a good experimentalist, but suppose you could, put in water and then you put in deuterium or something, okay, in there. And they're going to have a really low activity coefficient, right? It's going to be pretty much like a mixture, and then you can follow the radiolabeled, molecule, and you can observe it. Okay, I know a little bit more about how they do this in, say, colloidal systems. You can use fluorescence microscopy, and you can actually fluorescently label molecules like DNA or small particles. You can watch it diffuse around. Okay, so you can watch a single tracer. Mutual diffusion coefficients are harder to get. You can do things like look at how two interfaces fuse together. There's other ways to go about getting it, but so it's just kind of an important concept to notice the difference between a mutual diffusion coefficient, which is an inherent property of the mixture, right, and then the self-diffusion coefficient, which is just a property of a single. Questions about that idea? Good. Okay. Not that complicated, but kind of fun. All right. Oh, by the way, I did a derivation of that expression that I have that relates to two fusion coefficients. I'll put it on the web. It's not that complicated. A little bit thermal. But I thought it'd be fun to put it. Okay. Well, let's do two. Right, total mass flux. So just like we saw with our other two cases, we want an expression for the total flux. And currently, we only have the diffusive flux, right? We want to take into account convection as well. So let's add convection. So we've kind of been doing this already. This one's probably easy to see. We've been using this case on total mass flow, right? So we said total mass flow looks something like mass flow rate is rho Q, right? And I said, well, we kind of need to talk about it through the surface where we've got some unit normal. And so I said, we can rewrite that as rho V dot the unit normal times an area, right? So I say, this flow rate, this volumetric flow rate for here is really going to be the velocity times an area, but we're going to use a dot product, we'll take the orientation, maybe the velocity. This, right? So we have some velocity vector that we're going to use to add that up. And now what we want to do is look at just an individual species mass flow. So for an individual species, it looks pretty easy. We're just going to take a little subscript A on it, and the whole thing, or let's see, the book does an alpha. For some reason, you really like that, so we'll do alpha. Rho alpha Q, and now we get rho alpha B dot NA. Okay, I guess we should say that's the area of that surface. Okay, and now we say this right here, we can identify that as the mass flux. Okay, and so we can write a combined mass flux then. Combined mass flux, which is equal to a given expression N in first year on my foot, so a little n for this case here, which is going to be rho alpha v plus little j alpha. Okay, and that's the total, or what do they call that? The combined mass flux vector. Mass flux vector. All right, hopefully that's pretty straightforward. So I'm going to make a couple of comments about this, but I'll pause here and see if there's any questions about this. Does this feel good? All right, so let's make a few comments. Okay, so the first thing is we can show something about these diffusive fluxes if we think about it for a minute. So first thing is that the total mass flux is rho v, right? I just said that right there. Okay, so if that's the case, then just think about that. So if I add my total fluxes here, if I have NA and NB, I add them up, I can rewrite that as rho A V plus JA plus rho B V plus JB. Okay, and if rho A V plus rho B V plus JA plus JB. Right? Now this quantity here, this is my rho V, right? So this is the total velocity, right, of the system. So that means that my total mass flux is that, and my total mass flux is that. Then these two guys must add up to 0. Okay, so JA plus JB equals 0. Okay, so that's the first comment. So that makes sense, I think, right? If I have diffusion of A, I have to have diffusion of B be equal and opposite. So diffusions are equal and opposite in the binary. Okay, so if this were like a ternary system or a quaternary system, we'd still find that the flux is sum to 0, but then they're not equal and opposite because there's more than one component, but they still have to all sum up to 0. All right, comment 2 will be, there's another way to think about these fluxes using a species velocity. So another way to think about this, okay, and this uses this idea. So suppose I have, suppose I have this box that I have before, okay, where I've got A in it, I've got these. Okay, I can think about just the velocity of a species all by itself. Okay, so I can say there's some velocity of B in here, and there's some velocity of A in here, right? They're moving relative to each other. Okay, so this I'm going to call a species velocity. Okay, it's just the average of all the molecules, right? So if I just take only A's, add them up, look at how the molecules are moving. That's just the velocity of the A's. Okay? So if I think about that, the total flux must also then be equal. So the total flux must also then be rho rho alpha v alpha, right? Because I'm saying if I have a species velocity, v moving that way, then the total flux has to be, the density times that species, okay? So we want to then kind of relate this back to these expressions and put it together in terms of a species velocity. So the convective flux is still this. This is still our convective flux here. Right? This is our convective one. So one of the things that we need then is to think about, well, how do I get the total velocity from these species velocities? So the book defines a couple different kinds of velocities by weighting the species velocities differently. So the classic one is the mass average velocity. Okay, that's the conventional velocity you're used to thinking of. And that's just the sum of the mass fractions multiplied by the species velocity. So overall alpha. So in this case, that would be, WAVA plus WV. Okay, you're just weighting each of these species velocities by how heavy they are relative to each other, right? To give you the total velocity of the system. Okay, so when we do that, we can rewrite J right here. So if I have J alpha, I'm going to copy that expression over there, but I'm just going to move rho v to the other side. So that's going to be N alpha minus rho alpha v. Okay, but I just said N alpha is this guy right there. Okay, so I can say that is the same as rho alpha v alpha minus rho alpha v. So I can rewrite JA as rho alpha times v alpha minus the mass average velocity. Okay, so you can stick on there. Okay, and this is sometimes called the diffusion velocity. Okay, all this is telling you, right, is that I've got some convection that's pushing stuff around, and diffusion is what's, going against, or with convection that's extra, right? That's pushing that species around, right? So there might be some flow here that's pushing everybody along, but those gradients are making A move a little bit faster than the flow of everybody, and B a little bit slower, right? Relative to that background, because there's still a gradient there, okay? So this diffusion velocity is telling you that, I have this species velocity, that's just what that's going, right? Relative to the bulk. And that diffusion has to be equal to that difference. Does that make sense? So maybe another way of thinking about that is the takeaway is that at the end of the day, all the velocities, all these species velocities have to add up to give us that convective velocity, right? But they may cancel out each other. One might be moving a little bit back relative to the other, one might be moving a little faster. They all kind of cancel out that velocity. Okay, so the book has tons of these expressions that relate species velocities on this, and that. We're going to talk real quick here about molar fluxes too. That's what makes this, mass minimum gain too, because there's just tons of these different kinds of expressions. But it doesn't. There's really nothing conceptually difficult. It's all notational, okay, in that sense, right? So if this makes sense to you, right, same way we did the other one, that's fine, okay? The species velocity is a way to sort of think about it a little differently. It's sort of another way of thinking about these fluxes. You can sort of go back and forth between thinking about bulk flows and species flows. Almost always when we think about velocities, we're going to be talking about, these kind of velocities, all right? But sometimes it's useful to think about these species velocities in an extra way, but there's nothing conceptually new about that. Question about this? I don't know if I explained it too confusing.
The diffusion velocity is V alpha minus V.
I think this, that's a good question. I was under the impression that it was, yeah, this is the diffusive velocity, just this part. You're right. Thanks for clarifying. Because this is the diffusive flux, right? So you're right. Thanks for mentioning. Okay, I have one more component to make. Unless there's other questions. Component 3 is about molar units. Okay, so it's sometimes convenient to use stuff on a per mole basis rather than a per mass basis, especially if you have chemical reactions, right? So, you know, if you're doing stuff without chemical reactions, it's usually easiest to just stick with mass, but you know, sometimes you gotta do that. So, units in moles, there is C, which is the total molar concentration. Right, so that's going to be like moles per volume. Right, this is, you know, sort of analogous to rho, right, which is our total density. And then we're going to have a C alpha, which is the species concentration. Okay, that one's analogous to rho alpha, right? And then the other thing we have are mole fractions. And those are analogous to our mass fraction. Okay, and so then once we've got those guys, we can rewrite the same fluxes that we did, but now there's a little bit more notational pain. So I'm going to put here, right here, the average velocities, and I'm going to write over here the species velocity expression. Okay, so these are these, you know, we just talked about this other way of thinking about this. I'm going to write down the diffusive flux, the convective flux, and the total flux. Right, so the diffusive flux, they use a capital J for the moles, and then they also put a star. Now, I don't remember, I think it's like, they have this mixed one where they have fluxes with relation to the mass gradients. And like, anyway, they have these mixed expressions, which I don't know when those arise and why they decided they wanted to put them in. It's a super big pain. Okay, so here now we define the diffusivity, right, in terms of there's a concentration up front instead of a rho, and the gradient is in the mole fraction instead of mass fraction. That's the diffusive flux there. Or we can rewrite this with the species velocity as CA V alpha minus V star. Okay, this V star is the mole average velocity, right? So that's mass average mole average velocity. Okay. I think one of your homework problems, if I remember right, is to just do some of this practice of relating these expressions to each other. Okay. Some of this is probably, I hope this is not like too confusing. It's like just a lot of bookkeeping. So hopefully a little bit of practice with this will help you feel a little more confident just as you write these things down. And hopefully also some of the analogies help you remember, right? Because this expression, like I don't remember, you know, like two different expressions for say the species velocity or the diffusion velocity relationship, right? You just kind of remember, oh, yeah, there's this, you know, subtraction here, and then when there's moles, these are moles, and when it's, you know, masses, these are masses, and that's kind of good. Okay? So the convective flux is C alpha V star. That's the same, so this is the same between these guys. And then for the total flux, they use a big N alpha, which is now J alpha star plus C alpha V star. And over here, this one is C alpha V alpha. Okay? So this is, again, this, I don't know if that's, whatever you write down this, and this is C alpha V alpha I. Yeah. Okay? So the species velocity multiplied by the concentration. Again, these are all in your book. You can look them up. So if you're confused about specific notation, look at that. Try to copy the book's notation. Keep it strictly. All right, last thing. 10 minutes. I think we're gonna finish this. Okay, so the last thing is transport properties. We talked about this last time. So now we're just going to talk about transport properties for mass diffusion. So first thing was we gave just some examples just to get a feel. So if you remember, we talked about gases and liquids and solids, and so we can give ourselves some idea here. So maybe a typical gas might be water, nitrogen mixture. So that's going to be like water and air. And so this will be a gas. And the diffusion coefficient here is 0.259. And this is in centimeters squared per second. Okay? So this one was at 308 Kelvin, I think, in 1 atmosphere. So note the units here too. This is a length squared per plane. All our diffusions are in length squared per plane. So when you're thinking about kinetic viscosity or thermal diffusivity, you should all do that. And if I have a liquid, this is, say, ethanol and water. This will be 0.743 times 10 to the minus 5 centimeters per second. This one is at a mole fraction of ethanol, 0.68. Okay, so notice we dropped a lot in the diffusion coefficient from gas. So gases choose to diffuse around them. So maybe a better unit for this might be microns squared per second. So this is 743 microns squared per second. So it's maybe a little bit bigger, but if you think about these guys are moving around, you know, centimeters length scale, okay? And these are diffusing around micron. Okay, and then solids. This one is this was helium and silica, which is what we did earlier today. This one is 2.4 times 10 to the minus 10 centimeters squared per second, which is 2.4 times 10 to the minus 2 microns squared per second. Okay, so this is like, you know, maybe this one's hundreds of microns squared per second. Now this is, you know, less than a micron squared per second, right? So nanometer scale diffusion around. Okay, so that's just to get some feel for that. We also looked at this pressure and temperature behavior to get an intuition. And so this is for a self-diffusion coefficient, rho, they will just be, I think in the book they have DAA star, okay? This A star because it's a tracer diffusion, right? So they measure something that was, you know, A star in A, okay, with their tracer, and this is relative to the critical value for the number. A star, and then this was these corresponding state plots. We talked all about this. I'm not going to go into the detail about corresponding states and all that kinds of theories again, but the basic idea here was there's a curve like this, and then there is a two-phase region and then a curve that sort of comes off here. And so up here, this one sort of flips. This one is the vapor up here, and the liquid is down here. And so increasing pressure is in that direction. So that's increasing in that direction. And so what we can get from this, so we think about a gas and a liquid, what happens with temperature and pressure. We stare at this for a minute. We see that as temperature increases going this way, okay, the diffusion coefficient is going up. Okay, so that's for both cases. So as temperature goes up, we have TAA is going up, TAA is going up. Okay, but then as pressure is increasing, the diffusion coefficient is going down. Okay, so pressure is increasing. Okay, and there is a low pressure limit up here. So you can't see this in my drawing, but essentially, like as you're going down in pressure, right, you reach this line where everybody stays the same. So in a gas, you go down to a low pressure limit. Okay, that's what I'm thinking up there. Okay. So the sort of last thing to say is that there are the same four things we can talk about for diffusion coefficients that we can talk about for other things. So there's experiments, there's corresponding states. So, I guess we'll just put that 4 ways. To get TAP. Okay, so experiment. There was corresponding states. There was kinetic theory. Okay, and simulation. And in kinetic theory, there was the same Maxwell-Boltzmann and Chapman-Enskog, right? So we had this Maxwell-Boltzmann in here. So you can go back and look at those notes. There are 2 N's in Boltzmann. There's Chapman-Enskog. Okay, and the Maxwell-Boltzmann, right? That was the hard sphere case, right? And then the Chapman-Enskog as in the Lennard-Jones potential, okay? And then, so this was for gases, okay? And then there's one for liquids, okay? And this is called the Stokes-Einstein. Okay, this one's for liquids. And we don't have time to talk about it today. You can read about it in your book, okay? But, how in every case inverts are like, right? They keep repeating these ones for gases and for liquids they do one random. We had one by Eyring, and then we had one by the other guy, I can't remember the name, with the lattice theory, space down. And then Stokes-Einstein, okay, is one for diffusion. And this comes from that paper that Einstein published in 1905, right? And the expression I'll just write up for you is the diffusion is equal to kBT, which is Boltzmann's constant for temperature, divided by some constant times pi mu r, okay? Where, so this he derived for a colloidal system for like a large particle, okay? And so r here is the radius of that particle, and this c is just a constant, and it's either a 6 or a 4. It's a 6 when you assume no slip on the surface. That's where the Stokes part comes in because you get a Stokes drag on the particle. Okay, it's a 4 if you assume slip. So this is no slip. That's fast. Okay, so if you have questions about that, ask me next time. We can take 5 minutes. All right. So thanks for your attention and good luck. We'll talk next time about shell balance.